This presentation is for the World Congress on Sustainable Technologies, WCST 2015. I am Hooriya Anam, and with me I have Awais Shafique and Arsalan Javed. We are a team of electrical engineering students from National University of Science and Technology, Pakistan. And we are here to present a research paper titled as a low-cost functional electrical stimulation technique for the essential tremor suppression using off-the-shelf components. Now let's begin with our presentation. The motivation behind our research work is that there are about 281 million people which are affected by tremors. And among these tremors, essential tremor is the most common neurological disorder. It causes an involuntary rhythmic shaking of the particular parts of human body, and its frequency range is from 3 to 12 Hz. Among the essential tremor, the hand tremor is the most disabling tremor, and the patients unfortunately become unable to perform even the simplest tasks of life. This continuous involuntary motion makes the patient's life difficult, if not impossible. And even after such medical advancements, the true cause of essential tremor is still not understood completely. Our paper focuses on essential tremor, which affects around 220 million people in the world. And although this tremor is very common, yet its root cause is still unknown. According to the International Essential Tremor Foundation, currently there is no medication that has been specifically designed to cure the essential tremor. And it occurs at any age, and it also gets worse with age. And genetics is thought to be responsible for causing essential tremor in half of the patients. This form is referred to as familial tremor, and a child with patients having essential tremor has up to 50% of the chance of inheriting the responsible gene, but may never actually experience these symptoms. Although there is no proper cure for curing the essential tremor, yet there are some solutions which can temporarily reduce the effects of essential tremor. One of these solutions is medication. And although no specific medication has been designed for essential tremor, yet there are some medicines for the Parkinson's disease, and it may be combined in certain ratios to be given to the essential tremor patients. The ratio in which these medicines will be combined is of crucial importance here, because ladies and gentlemen, God forbid, if they are combined in the wrong amount, then it will worsen the tremor. And even when they are given in the right amount, your body actually becomes immune to these sort of medications, and in either way the medication becomes a lifelong hassle for the tremor patients. For more permanent solutions, the patients move towards surgical procedures such as the deep brain stimulation. It involves the placement of electrodes in the thalamus region of the brain, and these electrodes are connected to an electrical pulse generator. The current pulses generated through this implanted electrical pulse generator are then used to regulate the brain waves, and in turn this whole process aims to control the essential tremor. But the surgical procedure also comes with a price, because the surgical complications of the deep brain stimulation include intracranial hemorrhage, infections, seizures, internal bleeding, and may lead to side effects such as depression and suicidal thoughts. This procedure has found to lead to actual suicide in certain cases. Some assistive devices have also been designed to help the essential tremor patients carry out their daily life activities like eating and drinking with ease. One of these devices is liftware. It consists of a stabilized handle that gets attached to different utensils. These utensils then shake 70% less than that of the hand which is holding them, and owing to their tremendous contributions in the lives of essential tremor patients, Google acquired LiftLab, the company that had designed this device, in September 2014. Other devices that have been made on the same principle are mentioned here, like the weighted writing pens, the wrist weights, the stay ball, and all of these devices have this downside that they are limited to only a limited number of applications. Now we move forward to the shortfalls of the existing solutions that we have already discussed. First of all, we come towards the medication. As I've already said, that medication ultimately becomes a lifelong hassle for the essential tremor patients. Moreover, there is no acquisition and suppression device available in the market in the form of a product. The proposed circuits for such acquisition or suppression are either bulky, expensive, non-wearable, or high cost. These assistive devices, which have been designed to help the tremor patients, are also only limited to some applications. So we move forward to a better suppression technique, that is functional electrical stimulation. In the light of such circumstances, a novel technique known as functional electrical stimulation has been employed for essential tremor suppression. The technique has been previously used to improve the movement control in stroke and paralysis patients. Functional electrical stimulation is a form of therapeutic treatment that applies transcutaneous high voltage and low current pulses to initiate contractions in muscles and is commonly used for individuals with spinal cord injuries. Functional electrical stimulation has been used previously to facilitate upper and lower mobility, improve the respiratory function, restore bowel and bladder function, and to treat and help prevent secondary complications. Now we move forward to some of the reasons that why we have used functional electrical stimulation technique for essential tremor suppression. Some of the reasons for using FES are that it provides hand stabilization. It doesn't hinder your voluntary movement. It enhances the patient's grip over the objects that he's trying to hold. It helps in muscle building, and it is not only limited to wrist tremor. Now we move forward to the literature review that we carried out for the functional electrical stimulation technique. First of all comes a research paper written by Professor Zhang and Professor Vitek Ang. It is titled as the reciprocal EMG controlled FES for the pathological tremor suppression of the forearm. For this paper, they designed an assistive system used to attenuate the tremor with the minimum impact on the voluntary movement. They used surface electromyographic electrodes for the feedback. Also, the important assumption used in this paper was that they proposed a novel two-stage filter. The first stage removes the FES contamination from the raw EMG signal, and the second stage is used to separate the voluntary movement from the involuntary movement. An important assumption used in this paper was that the voluntary movement only exists below 1 Hz of frequency. Carrying his research work forward, Professor Zhang wrote another research paper which was titled as the Neural Oscillator-Based Control for Pathological Tremor Suppression via Functional Electrical Stimulation. He worked on the same system and introduced a neural oscillator-based control. The important functions of this neural oscillator-based controls are regulating the frequency pattern of the controller and regulating the phase of stimulation. Owing to his tremendous contributions in the lives of essential tremor patients, he received a Delsus Prize for this paper in 2011. While Dr. Zhang was working on achieving Delsus Prize, Professor Vitek Ang worked along with a team of researchers on an anti-phase tremor attenuation system and wrote another research paper which is titled as Using Electromechanical Delay for Real-Time Attenuation System Using FES. He used surface EMG electrodes and accelerometers for the tremor detection. An important conclusion of his paper was that the surface EMG signals are very useful when it comes to predictive algorithms because these signals precede the actual joint movement by 20 to 100 milliseconds of delay. So it gives us ample time to perform signal processing and generate an anti-tremor signal through FES. And according to his experiments, the results show that 57% reduction in tremor power was achieved in one of the tremor patients. Literature provides us with an option of different stimulation waveforms. Now these waveforms may be of different shapes and can be monophasic or biphasic in nature. But the most preferred of these waveforms is a scale wave. Now why do we use a scale wave for the functional electrical stimulation technique? The reason is that the scale wave penetrates the body in a more efficient manner. Like some of you may be familiar with the transcutaneous electrical nerve stimulation or TENS device. Scale waves are also implied in TENS devices for pain relief. For our initial design presented in this paper, we have used a monophasic scale waveform. Now why have we used this waveform? That is because it is generally used for wound healing. But later on, we moved towards a biphasic symmetrical waveform because it is more comfortable and it stimulates a pair of muscles rather than a single muscle, and thus it causes less fatigue. Most of the literature on FES utilizes transformer-based circuits to produce high voltage and low current pulses, so we have done the same. We have initially used a buck converter with a transformer and a digital feedback for digital controllability of the output along with the load regulation. For suppressing the essential tremor, we have used a transformer to step up the voltage to a maximum of 90 volt peak to peak when it comes to biphasic waveforms and 45 volt peak to peak when it comes to monophasic waveforms. The high voltage is required to reduce the human skin resistance and allow the current to flow easily to stimulate the nerve controlling the muscles. Our circuit design basically comprises of three major modules. The first one of which is a buck converter. As I've already told you that the buck converter is using some switching modifications and it operates on a battery of 9 volts. The converter has been designed using easily available electrical components and it can step down the voltage to 2.7 volts on a duty cycle of 30%. For the feedback and control circuitry, an Atmega 328P has been used to provide the digital feedback for load regulation and the digital controllability of 3 factors. Now what are these 3 factors for the digital controllability? These are frequency, amplitude, and the pulse width. And the voltage divider samples the converter output and feeds it to the analog to digital controller of the Atmega 328P. A smart algorithm compares the sampled voltage with an internally stored reference voltage and automatically changes the duty cycle of the control 1 signal to match the output voltage of the converter to the desired reference voltage and hence providing load regulation. The control 2 signal controls the pulse width and the frequency by switching the load switch. The feedback from the IMU given to the controller is actually used to find the frequency and the amplitude of the actual raw tremor signal and then controls the output of the FES circuit by varying this control 1 and control 2. The third most important module used in our design is a load switch and a transformer. The load switch is actually a combination of N-channel and P-channel MOSFETs. The transformer used is a commercially available transformer which has 300 mA current and 12 volts AC transformer. The transformer steps up the voltage to a maximum of 82.5 volts with a duty cycle of 1, that is 100%, and the Vin for the transformer is 9 volts. Now, this high voltage is required to reduce the human skin resistance. The outputs actually show. These outputs are the outputs of our experimental results. And these outputs show that with a duty cycle of 60% for the control 1, the output of the buck converter is 5.4. And the voltage across the load is stepped up by the transformer to 49.5 volts with a pulse width of 250 microseconds. Now, why have we selected this 250 microseconds pulse width? This is because it is written in some of the researches that the 250 microseconds is optimum for the muscle stimulation, and it is controlled by the duty cycle of control 2. When it comes to the cost analysis, we have overall estimated the cost of our device to be in Pakistani rupees 586, whereas in US dollars it comes out to be $5.61. The proposed functional electrical stimulation circuit is designed based on the human body stimulation standards for the FDA approved devices. It has been developed to match the device specification of EM41. The proposed circuit is superior to that of device and other proposed circuits because it has the ability to digitally regulate its output voltage and the frequency automatically using the IMU feedback system. Moreover, the controller ensures that the pulses are out of phase by sending predictive electrical pulses based on the frequency extracted by the IMU feedback for optimum tremor suppression. Some of the specifications of the FDA approved devices are to be shared with you, that the output voltage should be maximum 90 volts peak to peak. The current should be 180 milliamperes peak to peak. The frequency should be 1 to 120 Hz. The pulse width should be 250 microseconds, as I've already told you that it is most optimum. And the load is 500 ohm because the high voltage reduces the resistance of the skin. The curves show a relation of pulse width to the current required for muscle stimulation using a pulse width of 250 microseconds for optimum stimulation according to research. In conclusion, a cost-effective system for the suppression of essential tremor based on the functional electrical stimulation of the nerves is proposed. An exact anti-phase signal of the tremor is generated in the form of a monophasic scare wave pulse through the novel functional electrical stimulation technique. Owing to the inertial measurement sensor units that we have used, it is ensured that the pulses perform out-of-phase cancellation of the tremor signals. The two parameters that are on prime focus are the cost effectiveness and the prefabrication. The former is achieved through the non-invasiveness of the proposed procedure, whereas for accomplishing the latter, the idea of using off-the-shelf components is chosen in order to ensure the stability of the design system in real time. The future works will be focused on creating a complete prototype of the essential tremor suppression device by integrating the already existing module with the tremor acquisition module and other type of circuitries. Now our presentation has come to an end. I would like to thank you all and the World Congress on Sustainable Technologies for letting us present our proposal to you people. For any questions, please email us at the email address shown.